All right, welcome. This is section 3.1 for Algebra 2. In this chapter, we're looking at solving systems of equations, and today's topic is specifically solving a linear system using a graph or a table. So take a minute and write that objective down in your notes. Keep in mind that you can always pause these videos at any point if you need to catch up. All right, so a system. It says when you have two or more related unknowns, you may be able to represent their relationship with a system of equations. It's simply a set of two or more equations. When we solve a system, we are looking for a set of values, in other words, an XY ordered pair that makes both equations true. So our first example, we have a system of two linear equations, and we're going to look at solving it two ways. The first method is using a graph. So if I were going to graph these equations, I would start out putting them in slope-intercept form. So the top equation here, I'm going to add the 3x to the other side and then divide everything by 2. And then for the bottom equation, I'm going to subtract the x to the other side and then divide by 2. All right, and then I'm going to grab my graphing calculator. We certainly could graph these by hand, but at this point, our second method is to use a table, so it's handy if we have these already in our calculator. So let's go to our graphing calculator. And we're going to go to our y equals screen. I'll clear these out here and show you. So our first equation is y equals 3/2 x plus 4. So 3 divided by 2 times x plus 4. Our second equation, we need negative 1/2, so negative 1 divided by 2 times x. This time it's minus 4. Okay. Now, for the window, we can use a standard negative 10 to 10 window, and the fastest way to do that is to type in a zoom 6. It resets the window to a standard window. And there are my two equations. And what I'm looking for on the graph is the point where they intersect. So from our larger picture over here, you can see that they intersect at the coordinates -4, -2. That means that's the ordered pair that works in both equations. And we could certainly take time and plug that into each equation to verify that it really does work. All right, the second method is to create a table. And so what we want to do, our calculator keys, we're going to actually enter those two equations, which we just did. But now we're going to go to our table, and we're going to look for where they match. In other words, we have a table of values, but because we have two equations in there, we're actually going to have two different y values for every x. So we're going to start looking here, at 0, 1, 2, and we want to keep going. And what we hope to find is a place where they match. Okay? So let's go to our table. So second table, and notice now my table is all messed up because of a previous example, but we can start the table anywhere we want. So let's go to table set, it's second window, and let's say I want to start at 0. And I can scroll up and down from there. And let's go back to table now. And we're looking for a place where they both intersect, where they have the same y value for the same x value. And from our graph, we know that it should happen at -4, -2. And so if we scroll up to that, what we're looking for here is the fact that when x is -4, the y coordinate for both is -2. And so that is proof that the two graphs intersect at that point. All right, let's look at another example. This one says, the diagrams show the birth lengths and growth rates of two species of shark. If the growth rates stay the same, at what age would a spiny dogfish and a Greenland shark be the same length? Notice the directions here tells us to use a table to solve this one. So we have to get two equations so that we can enter them in our calculator. And if you look at the information over here, when they talk about how fast it's growing, that's basically your slope, your rate of change. And the birth length is your starting value, or your y-intercept. Okay? So for the Greenland shark, our equation would be y equals 0.075x plus 37. And then for the spiny dogfish shark, our equation would be y equals, our growth rate or slope is 1.5, and then our y-intercept here is 22. All right, so both of them have a positive slope, but they have different starting points. So if we were going to draw a rough sketch of this, one of them is starting here at 22, one of them is starting at 37. Okay, but they're growing at a different pace. So the one starting at 37 is growing slower, has a more shallow slope than the one going at 22. So eventually they would intersect, and that's the point we're looking for. But we're going to find it with a table. So again, we're going to enter two equations. We'll let this top one be y1, the bottom one here y2. All right, so you can pause the video and go ahead and enter that on your calculator if you need more time. So I'm just clearing out my old ones so that I can enter this new one. All right, and then we're going to go to the table. And we are looking for where they have the same value. And if you look at it, both of them are increasing, but they are increasing at slower rates, or one is slower than the other. So eventually we will get to a point where they have the same y coordinate. All right, we're getting closer here. Let me check my equation here. I'm sorry, I have the wrong, this should be 0.075. That's why they're not intersecting. Let's go back here and fix that. Now we can go to our table. That looks a little better. All right, so going down here, notice that at 20 years, they both have a length of 52 centimeters. Okay, so when x was 20, our y values were 52 for both of them. Okay, so that would be the point of intersection or the solution to that system. Okay. In our last chapter, we learned how to use a linear regression or that line of best fit. The difference today is we are going to look at two separate sets of data, and we want to find that point where they intersect. So in this problem, it says the table shows the populations of the New York City and Los Angeles metropolitan regions from the census reports for 1950 through 2000. Assuming these linear trends continue, when will the populations of these regions be equal, and what would that population be? So what we're going to do is we're going to create three columns of data. Our first one, our list one, will be our years, but we're going to start out with 1950 being year 0, okay? And then 1960 would be year 10, 1970 would be 20, etc. Okay, so we're going to enter that as our list 1. And then we're going to put the New York City data in list 2 and the LA data in list 3. Okay, we're going to shorten this up instead of using such huge numbers. Where it says 12,911,994, we're going to enter that just rounded to be 12.9. Okay, so we'll just do the millions part and then that first number after. All right, so grab your calculators. We're going to go into our list. So we need to do stat, edit, And our first list, remember, would be the 0, 10, 20, etc. Okay, and then our second set, remember, we're going to round things. So that first number is going to be 12.9. And we'll just know that everything is in millions. All right, our second number is going to be 14.8. We'll round up. Next we have 16.2, 16.1, 18.1, and 21.2. All right, and then let's go ahead and enter our LA data as well, the same way. So our first number would be 4.4. Next we'd have 6.7, 7.0, 11.5, 14.5, and 16.4. All right, so we have all our data in there. We're going to create two linear regressions. All right, so we're going to go stat, calc, number 4, linear regression. We'll start out with list 1 and list 2. And remember how we store our equation? We go to variables, y variables, function, y1. Okay, and then calculate it. Okay, so my first equation for the New York City information, y1 equals 0.147x plus 12.886. Okay, now we're going to do the same thing. We've stored that in y1. Notice our correlation coefficient is 0.96, so a very good fit. And then we're going to create a second linear regression. So let's go back to stat, calc, linear regression. But this time we're going to swap out the New York City data for the LA. So we're going to still use list 1 for our years, but now we're going to switch and use list 3. So I'm going to change the list 2 here, second 3, make it an L3. And this time when I store variables, y variables, function, but this time I'm going to move down and store it as a y2, as my second equation. Okay, and then I'm going to calculate that one, and I end up for LA with y2 equals 0.251x plus 3.805. Okay, so I have my two sets of equations here, my system, and I want to find where they intersect. Okay, so the keys on your calculator for this, we have to do second and then our trace key. Okay, so the second key, then the trace key. And then we're going to choose number 5, which says intersect. And then we're basically going to hit enter 3 times. It's allowing us to make a guess, but we don't need to do that. Okay, so let's go back to our calculator. We also want to set a window. So I'm going to change my window here, and I'm going to go from 0 to 100 for x. And I'm just going to take that scale out. I don't need the tick marks. And then for y, I'm going to go 0 to 30. I don't need to be super high. My y-intercepts are pretty small. But again, I'm not going to worry about the tick marks in there. Okay? And then we're going to graph it. So we've got our 2 lines, and we are trying to find this point where they intersect. Okay, so again, we're going to do second trace. We're going to choose number 5, the intersect. And then notice at the bottom here in black, right under my window, it says first curve. We've entered 2 equations, but there's room for 10 equations. So it's basically just saying, tell me which 2 you want me to have intersect. So the first curve, the question mark, the cursor's on the first one, that's fine. Hit enter. Then it's asking, is this the second one you want me to use? Hit enter again. Then it asks if you want to make a guess where they intersect. You can just hit enter to bypass that. And then at the bottom of your screen, you should see the coordinates of that intersection point. All right, so it's at about 86.8. And 25.6 would be the intersection. Now remember, this 86.8 is years. And remember, the 25.6 is in millions because we changed all that data. Remember, we rounded it to millions. So what we're really finding out here is that after about 87 years from that starting point of 1950, if we go out 87 more years, which puts us at 2037, they will have the same populations and that value would be about 25.6 million. Okay? All right, so we've been looking at solving a system either using a table or graphing it. Again, we can be graphing it on our graphing calculators at this point. The last thing we want to look at today is classifying systems. So we classify 2 linear equations by the number of solutions they have. A consistent system, okay, the word consistent means there is one or more solutions. So it has at least one solution. Okay, so within a consistent system, we have 2 types. Independent means there is exactly one solution. Okay, so there's only one solution. A dependent system is going to have infinitely many solutions. Okay, so we can say a system is consistent independent, or we can say it's consistent dependent. The other type is an inconsistent system. That's one that has no solution. All right, so looking at these pictures, this one is consistent because it has a solution, but since it only has one, it's called independent. So consistent, independent would be 2 lines that actually intersect. This one is consistent as well because it has an overlap. It's basically the same line. We have 2 equations that really mean the same line. So there's one on top of the other, which means every point on one line is also a point on the other. So we have infinitely many, which makes it dependent. And then if we have parallel lines, they never intersect. So there's no solution, which makes them inconsistent. So again, consistent means there is some kind of solution. Inconsistent, there isn't one. All right, so our last example for today, it says to classify without graphing. So what we want to look at is, can we tell from the equations, are these intersecting lines, are they parallel lines, or are they 2 equations that really represent the same line? So to do that, we need to compare the slopes and y-intercepts. So we're going to take each equation and get it into that slope-intercept form. So I'm going to add the 2x over and then divide out the 4. 2 divided by 4 would be 1/2, and then 6 divided by 4, we could reduce that to 3/2. Our second one, we had 8y equals 4x minus 12. We would just divide everything by 8 to get 4/8 or 1/2 x, and 12/8 we could reduce that to 4/3. So now we're going to look at our 2 equations And what do we notice? Well, they have the same slopes, okay? So they're either the same line or parallel, but since they have different y-intercepts, they can't be the same line. So, same slopes, but different y-intercepts would mean that we have parallel lines. Okay? And parallel lines do not ever intersect. We will never be able to find that point of intersection. So we say this is an inconsistent system. All right, so take a minute and complete your notes packet where there is a summary page. Remember, our objective today was to look at solving linear systems using a graph or a table. And then our homework assignment is listed here. Good luck.